Hello, my name is Asaf Nissenbaum. I'm a researcher and a process developer in Civan lasers. In the following presentations, I would like to show you and discuss dynamic beam laser solutions for aluminum die-casted applications. Briefly about Civan, we develop high-power dynamic beam lasers that are based on coherent beam combining technology. Civan was founded at 2008 and we currently deliver commercial dynamic laser systems of above 100 kilowatts. We work with leading industrial companies, tier 1 companies, and job shops around the world to develop new applications and new solutions for current issues. The dynamic beam laser is a novel laser system that enables control on the power distribution profile and melt pool dynamics. In the illustration, you can see the main components of our laser system: an amplifier cabinet that delivers a matrix of collimated beams into the optical head through which the beams are coherently combined into a single mode beam. The beam shaping is enabled through the control of the relative phase of each laser source, thus enabling the creation of endless types of beam shapes. If we outline the additional parameters unique to our beam shaping system, the main unique features of the Sivan laser is the ability to produce endless beam shape profiles and to execute them with frequencies reaching to 40 MHz. On top of that, we can combine several different beam shapes into a sequence, thus allowing to further tune the process for complex applications. Furthermore, since the focal plane position is electro-optically controlled, we can change the focal position up to the megahertz regime, for example, for a very thick materials application. Recently, die-casted materials have gained more interest due to several benefits such as mechanical properties, complex power geometries, production time, and so forth. However, joining of die-casted parts is a rather complex process that in practice is only achievable by a small number of joining methods, usually conducted in a slow process time. Therefore, a robust and fast process would be extremely beneficial for a large-scale production. We will not dive into the casting process itself, but briefly, for several reasons that depends on the dynamics of the casting process, as well as the additive used in the process, die-casted aluminum contains a rather large amount of entrapped hydrogen. In the welding process, at high temperatures, the entrapped hydrogen diffuses into the melt and upon solidification, remains as a porosity defect. Additionally, the pressure inside these pores is rather high and may cause blowout that degrade the weld quality. Our solution is based on several concepts that involve degassing the melt pool by high stirring, elongation of the melt pool length and size, and if needed, a fast repair process. This results in a low porosity, high quality weld. So how do we achieve it? The first solution would be stirring. Stirring will induce degassing of the melt pool, such that more gas will come out of the melt. The flow dynamics of the melt pool are crucial to drive more gas out of the melt pool. The ability to design a stir pattern, or a stirring pattern if you wish, and to perform it with a very high frequency allows improved removal of the gas pores from the melt pool. In the simplified illustrations, you can see a comparison between processes that are conducted with a dynamic beam and without a dynamic beam. In addition, and not less important, the lifetime of the melt is the window in which the gas can evaporate from the melt. Therefore, increasing the melt dimensions will increase the lifetime in which the gas can come out of the melt pool. In the simulation that you can see the effect of different beam shapes and even beam orientations on the dimensions of the melt pool. Through beam shaping, we are able to control the dimensions of the melt pool, to elongate it, and thus to allow more gas to come up during the process. So the Sivan laser allows not only more mechanically reliable parts, but allows the significantly expedited process time. Additionally, complex geometries are very well suited for this laser system. In the following case studies, we display two applications that require a completely sealed part. The first application is a heat exchanger, where we started the process with robust and large porosity, but upon tuning, we eliminated most of the porosity and the sample holds the required pressure. The second case study is a sensor case very similar to the first case study, in which we also eliminated most of the porosity and welded at 15 millimeters per minute, much faster than any alternative. The sample again holds the required pressure by the customer. So if we look at the comparison of an alternative joining method, we can see that Civan laser shines in most of the important parts, specifically in stresses in deformation, process time, geometry, and scalability of the parts. So to summarize, the Civan laser can deliver a cost-effective production method with a high-quality weld in a stable process that lets you to have a freedom of design. With that, I want to thank you very much.